Let's discuss the next topic in the syllabus, which is called sets. So the topic for the session is sets. What is a set? We have discussed about different sets. The word set has been most commonly used in mathematics in many of the topics. But what is a set? Before we start this topic, let's take some real life examples. When I just write, say for example, in the previous case, we have taken the natural numbers as 1, 2, 3, 4, 5, and so on and so forth. I said n is set of natural numbers. So what is the word set when I have considered the case of natural numbers? Is what derives the topic of the session. So a set is the collection of numbers. As I can clearly see here with n, the set of natural numbers is the collection of the numbers 1, 2, 3, 4, 5, so on and so forth till infinity. So I understand that if I collect some objects and put that in this symbol form, then the flower brackets, which we call them as flower brackets, then that forms a set. But there is a more mathematical, meaningful definition for a set when we enter more further into understanding a set. So let's see what are the two restrictions which limit the defining of a set. So firstly, when I go with the definition, my first limitation is that all the elements or objects considered must be related to each other. So they must be related to each other. Say for example, I take a geometric box. When I take the mathematical geometry box and I include a compass, a protractor, a ruler, an eraser, that's it. So these are the things which form a well-defined collection because all the elements are related to each other when I just have a geometric box. Even a pencil can be inside the geometry box. But when I include a watch inside the geometry box, then I don't say that the watch is related to the geometry box. Is how I understand the first limitation. For example, when I take the geometry box, instrumental box, then I have a pen, a pencil, an eraser, a compass, ruler, protractor. They're all part of the geometrical instrument box, which we use in construction of geometrical figures. So these are related to each other. So when they are written in set form, definitely form a well-defined collection of objects. Therefore, the first property which defines that the elements or objects which are considered must be related are very much related here. But say for example, if I include a wristwatch into this, may not form a well-defined collection of objects because a wristwatch inside the geometry box may not be a good idea because that they are very different and not related to each other. If we understand in the sense of geometrical instruments, a wristwatch is nowhere related to the geometrical instruments. Hence, inclusion of wristwatch inside the set of all these objects may not form a set. But excluding this, these objects or elements might form a set. So this makes us clear understanding on the objects considered must be related to each other. Secondly, when I pick the objects, I should be able to pick the objects inside the set. The objects or elements inside the set or elements should be able to be picked. picked up. So when I say the objects or elements should be able to be picked up, then this forms a very complex situation, because when I take the example of stars in the sky may not form a set, because it is very difficult to pick the different stars in the sky. There are infinitely many stars, so picking up of stars in the sky may not be a set, based on the second limitation of which states that the objects or elements should be able to be picked up. For example, stars in the sky may not form a set. So this doesn't form a set. But when I pick vowels from English alphabets, the vowels definitely can be picked from the 26 letters of the English alphabets, starting from A and ending with Z. But when I take the example of vowels of English alphabets can easily be picked, therefore the vowels form a set, the stars in the sky do not form a set. The instruments in the geometry box form a set, but when a wristwatch is included in the geometry box, does not form a set, supported with the limitation 1 and the limitation 2. So vowels of English alphabets, which are clearly A, E, I, O, U, is something which we already know in the English class. The vowels are A, E, I, O, U, forms a set of vowels of English alphabets, the 26 letters starting from A to Z. So with this clear picture, it makes me understand that a set is a well-defined collection of objects. So when I go with the definition, it says that a well-defined collection of objects is called a set. So here the two examples make us understand on what is a set and what is not a set. So let's see some more examples on deciding whether a given condition is a set or not a set. So for example, I start with few of the examples. To start with, set of all odd positive integers. So let me start with set of all positive integers. So it is a well-defined collection because I can pick the odd positive integers and they are very much related to each other. So let's see set of all positive odd integers. If I take this in the form of O 1, 3, 5, 7, 9 and so on and so forth forms the set of all odd positive integers, and this is very much a set. So let's take another example of set of all collection of all good students in the class. So this has to be decided on two different conditions. Students in the class are very much related because they are in one class, but when I say about good students, I think it is not easy to pick up who is good and who is bad. Judging of good and bad has various factors affecting the justification of good and bad. Therefore, collection of all good students in the class may not be a set because it is difficult to identify the good students exactly on mathematical grounds. Therefore, the collection of all good students in the class may not be a set because it is not well defined. This is not well defined, and therefore this doesn't form a set, but this forms a set because it is a well defined collection of objects. Now let me take an interesting example which we are going to connect with sets and also with presumed knowledge on prime numbers. So with an example, write the set of all even primes is my question. I want to write the set of all even primes. Now primes are very much related to each other because they don't have factors other than 1 and itself. Now I had to find the set of all even primes. So the answer would be definitely it is a set because it is a well-defined collection of objects and we can pick up the even primes out of all the numbers existing in real number system. So this is a set, but I want to find the set of all even primes. The answer for this set would be that there is only one even prime which we identify in the real number system, and that is 2. Therefore, this is the set consisting of only one element, that is 2. So the answer for this would be singleton 2 because we are going to discuss about what this kind of a set is called in the future classes. But the answer is set of all even primes. There's only one even prime in mathematics, and that is 2, which is the least prime. The rest of the primes are all odd except 2 being the prime and also an even number. Now let's see the notation for sets because it is very important to understand the mathematical notation for the set. So every definition has its own notation in mathematics as decided by the famous mathematicians, and therefore every notation also includes the set with its own respective notation. So coming to the notation for a set, sets are generally denoted with capital letters or alphabets. So when I denote the natural numbers, I denote the sets with capital N, the set of natural numbers. When I denote the integers, I denote with the capital Z. So when I say Z, I say the set of integers because this is the notation I give for set of integers. When it comes to whole numbers, it is W, and when it comes to rational, it is Q. When it comes to real numbers, it is R, and when it comes to complex numbers, it is this. So sets have their own definitions in writing in this form. So generally the sets, what we write in the form of capital letters. Sets are generally denoted with capital letters of alphabets. For example, when I want to write set A, or I denote with B or C, etc. in writing the different sets. Or we can also write X, Y, U, anything but in capital form is what generally we denote in writing the sets. And not only that, the right hand side of the set is generally denoted with flower brackets. This is called the flower brackets. So when I write the set, we generally denote with the flower brackets. The elements are written in the flower brackets is assumed to be written in the set form. We don't use the any sort of brackets, but we use the, say for example, I want to write the set A in this form, makes me clearly understand that the elements 1, 2, 3 are written in the set form denoted by A. So A is the set consisting of elements or objects 1, 2, 3. The numbers in this case of an example. The other notation which we generally denote in sets, mostly in most of the cases of the problems, is belongs to and does not belong to. So we already have been using that in many of the cases, but because this is exclusively on the notation of sets, let's revisit the symbol for belongs to. Suppose I take the same example of A equal to 1, 2, 3, then I clearly identify that 1 is an element of A, 2 is an element of A, and 3 also is an element of A. But if I take any other element, say 11 is not an element of A because I can clearly see that 11 does not exist in the group of elements inside the set. So here we identify 3 elements to be the elements of the set A. Therefore, when I say the symbol this belongs to A is read as element 1 belongs to the set A is how I understand the symbol 1 belongs to A. So whenever I write 2 belongs to A implies I read this as 2 belongs to set A. When I take 7, I just write this because I clearly identify that there's no 7 inside the set. So this symboled with A implies 7 does not belong to A. 2 belongs to A is how I understand the notation for belongs to and does not belong to. 7 does not belong to A is how I understand the concepts. Now, continued with notations, there are two ways of representing the sets. One is the roster form and the other is the set builder form. So when I have sets, I can represent them always in two different forms depending on the demanded problems. One being referred as the roster form and the other being referred as set builder form. So what is the roster form? A roster form is the direct inclusion of elements in the set. When it comes to the set builder form, it is not the direct way of writing the elements, but an indirect form of representing in the set form. It will not be direct. We need to identify the statement and then write the elements in the roster form. So this is the direct step. This is including the indirect step. So let's see with more further examples to understand the roster and set builder form more better. So let's start with roster form. Now here, roster form is direct inclusion of elements in the set. Set builder form is the indirect inclusion of elements in the set. So the same thing when I write indirect inclusion of elements in the set. Now let me take one particular example which can be written both in the roster form and the set builder form. Say I take the situation of set of vowels. Say for example, I take the situation of set of vowels which I wanted to write both in roster form and set builder form. So when it comes to the roster form, the set of vowels which we already know from English topics that they are A, E, I, O, U, the 5 alphabets of the English letters which are called vowels. So here the roster form of set of vowels which I generally denote with A can be written as all the vowels listed directly in the set. So the vowels which are A, E, I, O, U directly written in the set form of A is called the roster form of writing the set of vowels. When it comes to the set builder form, the elements are indirect inclusion but not in direct inclusion. Therefore, the same set builder form of A can be written as X such that X is a vowel is how I write in the set builder form. So what difference do we find between the roster form and the set builder form is very important in differentiating between the two definitions which we have considered here. So when I take the set builder form, as I said, this is indirect inclusion, clearly makes me understand through this example of set of vowels that from this I don't get the complete information of the elements or objects inside the set. I have to just take this information and go a step ahead in identifying the elements. Now here it makes me understand with the outline of the picture indirectly that X is a vowel. Yes, set A is all elements X such that the condition is that X is a vowel. That means I get all vowels in the set form is what is the minimum information given by the set builder form. So immediately I can understand that from the set builder form, I can build the elements inside the set. Therefore, all the vowels A, E, I, O, U are immediately written in its intermediate step. Therefore, indirectly, set builder form derives the roster form from its minimum information provided inside. And this would be directly the roster form, is how I differentiate between the roster form and the set builder form. So let me take one more example where I take the set builder form and I want to construct the roster form of the given set builder form. So my A is X such that X is a natural number. My first condition is that X is a natural number, and not only that, the condition here is that X lies between this is the information given in the set builder form. It is not direct, but I want to generate the elements and then write in roster form. How do I do that is the biggest question in this problem. So let's start and see how we can do that. Now, as you can clearly see, the set builder form of the given problem, it says A is all elements X such that the first condition is that X must be a natural number. So whichever elements you're writing inside the set must be natural numbers, not other than that. And secondly, the condition is that we are going to consider the elements between 4 and 7, including 4, excluding 7, because this is less than or equal to, and this is less than. So inclusive 4, exclusive 7, I take all elements which are natural numbers, or I take all natural numbers between 4 and 7, including 4 and excluding 7. Now, once this information is grasped, I think it becomes very easy, because immediately I can understand that there are natural numbers between 4 and 7, and inclusive is 4, 5, 6, but exclusive 7, so I don't get 7 inside the set. So therefore, my set builder form, when converted to the roster form, gives me the set 4, 5, 6. The set with the elements 4, 5, 6 is what indirectly given in this form. So we should be able to convert the set builder form to the roster form, or sometimes the roster form into the set builder form. In this case, this being the answer for the given problem. So let's take an example problem where we are going to see how we can convert the roster form to the set builder form. And in this supporting example, we're going to see some interesting properties arising out. So to start with, an example problem where my roster form, say I take an example of the set X equal to this is the roster form. Now, in this case, I would like to take the different cases of converting into the set builder form. So firstly, what I do is I understand this clear picture of the numbers 1, 2, 3, 4, 5, etc. and etc. till infinity. So this is nothing but set of natural numbers, as we can clearly see out here. So I can write the set builder form of this with its first identification that this is all elements X which are natural numbers, is how I understand the set builder form of the given roster form, because each of its elements are natural numbers continued. So therefore I can write in the form X such that X belongs to N. But interestingly, I can also write this as X such that X belongs to the intersection of the natural and whole numbers. So when I intersect the natural and whole numbers, I get the natural numbers. So this also acts as the set builder form of the same given problem. Thirdly, further, I can take another set builder form for the same problem of set of all numbers starting from 1, 2, 3, 4, 5 till infinity. So if I write this in the form of X equals X such that X belongs to Z plus, then in this case I understand that the set builder form of the roster form need not be unique, but the roster form of the set builder form is always unique. it's very important to identify the uniqueness of roster form and set builder form. So as supported with, I get three different set builder forms which generally arise from one set written in its roster form consisting of elements 1, 2, 3, 4, 5. So I make a note here. So when I convert the roster form to the set builder form, the condition is that it need not be unique. As you can see here, three different set builder forms or more than three which can arise out of one set builder form, out of one roster form. So roster form when converted to set builder form need not be unique. But the set builder form when converted to the roster form is always unique. So set builder form when converted to the roster form will always be unique is the learning outcome in roster and set builder forms, in understanding the concepts of roster and set builder forms with their respective definitions. So when it comes to the roster form, which we already discussed with the definition and various examples, there are two important things we take into account when we write the elements in the roster form. So those are the two things which we're going to discuss. The first note is that the order of writing elements does not affect the roster form. Does not affect the roster form, because whether you write in one order or any other different order may not change the value of the set. Say for example, if I take the vowels A, E, I, O, U, it is not compulsory that I write in the alphabetical order, but I can randomly write this equally to be same as I, O, A, U, E. But both are again the same in the roster form, is how I understand the order of writing the elements in the roster form. Secondly, if I take the elements of the set are not repeated for few example problems. Now here, this makes me understand that the elements of the set are not repeated for few example problems. Say for example, I take my set is X such that X is the letters of the word Mississippi is one of the land on the globe. So X is such that X is the letters of the word Mississippi. Then in this case, when I write in the roster form, I don't include all the letters but which are not repeated. So if I have S repeated 4 times, I repeated 4 times, P repeated twice, and M only one letter, then I write only the letters of the word but not repeating them as repeated here in the word. So I identify the letters to be M, I, S, P, but not M, I, S, S, I, S, S, I. So here this comes as S, S, I, P, P, I. We don't write in this form with 4 S repeated, 4 I's repeated, and the repetition is restricted. So this is correct roster form. This is not the correct roster form. This is how I understand, with two limitations. One being that the order of writing does not affect the roster form, and the elements of the set are not repeated, which is taken as the strict limitation. So this is the roster form of this set builder form, but this is not the roster form.